All right, good morning, ladies and gentlemen. I know that I said I would not be posting a video today, but I realized that we hadn't really done much review on experimental design. So I just wanted to touch upon some of the key aspects. And the way we're going to do so is by going over an old AP problem. And I'll go into it in a little bit more detail than is required. So here we go. Of course, brought to you by Couch Potato Brand Snack Foods and Beverages. I am your host, Mr. G. By the way, I don't know about you, but whose hair is extremely out of control? I know mine is. I just can't get a haircut, these days. So I'm going to adjust this diagram of me to be a little bit more accurate. Granted, my hair is not this color, but that's just about what it looks like these days. Very out of control. All right, so this is the problem that we're gonna go over. So there's a biologist interested in studying the effect of growth-enhancing nutrients and different salinity levels in water on the growth of shrimps. All right, so how do these two factors, growth-enhancing nutrients and different salinity levels, how do those two factors affect growth on shrimps? So the factors are what we call the explanatory variables, and the growth of the shrimps, those are our response. That's our response variable. All right, so there's a large shipment of younger tiger shrimps from a supply house for use in the study. The experiment is to be conducted in a laboratory where 10 tiger shrimps are placed randomly into each of 12 similar tanks. So we have 10 tiger shrimps, groups of 10 tiger shrimps placed randomly into each of 12 similar tanks. So it's a little confusing, the wording here, but basically the idea is there are these 12 tanks, and in each of the tanks are groups of 10 tiger shrimp, and there they are right there. You can count them. That's 10 shrimp, very tiny. I wouldn't say microscopic, but they're small, so you can't really make out the size or any of the detailed features in this diagram here. Okay, that is essentially what we're working with. Okay, so the biologist is planning to use 3 different growth-enhancing nutrients, A, B, and C, and 2 different salinity levels, low and high. List the treatments that the biologist plans to use in this experiment. All right, so before we get into the treatments, I'm going to sort of break it down. So like I mentioned before, there are 2 factors, the nutrients and the salinity level. Each of these factors has some levels. And the levels basically are the values that this variable can take on. Think of nutrients as a variable. This variable can take on the value of A, B, or C. Similarly, think of salinity as a variable. Salinity can take on the values of low and high. And thus, the values that your variables can take on, your factors can take on, are what we call levels when we're talking experimental design. Now, putting that information together, we have a set of 6 treatments. So the treatments will basically be all combinations of all levels. For example, for low salinity level, we can pair each low salinity level with each style of nutrient, A, B, or C. So treatment 1, treatment 2, and treatment 3 will be A low, B low, C low. Similarly, we can pair each high salinity level with each style of nutrient. So T4 will be A high, T5 will be B high, and T6 will be C high. And those are your 6 treatments. I do recommend anytime you're stating treatment groups, label them. number them, do something so that if you have to refer to them again later on in the problem, they're clearly labeled and you don't have to write them out explicitly every single time. Okay. Using the treatments listed in Part A, describe a completely randomized design that will allow biologists to compare shrimp's growth after 3 weeks. Okay, so we're going to go into Part B in a moment. I just want to talk about what are the experimental units in this problem, because it's a little confusing, but I want to talk about in general how you determine what the actual experimental units are in an experiment. So you might think, oh, it's the shrimp that are the experimental units, specifically the individual shrimp. It's actually not the case here. So how you determine the experimental units is you ask yourself, what are the treatments being randomly applied to? And in this particular case, the treatments are going to be randomly applied to the tanks. And therefore, believe it or not, the tanks are the experimental units. Or really, since we're measuring shrimp growth, if it makes you feel comfortable, you can think of the groups, the individual groups of 10 shrimp as the experimental units. So it's not the individual shrimp, but you can think of it as the individual groups of shrimp. So the 12 different batches of 10 are your experimental units. All right. But the key there really to understand is that the experimental units are the items that are being randomly assigned to treatment groups, or vice versa. They are the items that the treatment groups are being randomly assigned to. They're equivalent statements. Part B. So a completely randomized design. That language, completely randomized design, implies no blocking. All right, so if you're asked to design or describe a completely randomized design, do not bring up a block. And I put it together in 3 steps. So the first thing I did, and this is always a really good first step, is to label each tank with a unique integer 1 through 12. In general, whatever your experimental units are, start out your random assignment by labeling each experimental unit with an integer from 1 to whatever. It doesn't even have to be random. That part doesn't have to be random. You're simply labeling them. The randomization process is going to come up next. So now we have each tank labeled 1 through 12. We're now going to use a random number generator, and we're going to randomly generate 2 unique integers between 1 and 12. Okay, and then I go on to apply context. So when you're describing a randomization process, make sure that at each step, you bring back the context of the situation. We're not just talking about numbers and random number generators. We're actually, these numbers represent something. All right, so these 2 integers that we've just generated, they will represent the 2 tanks that will receive T1. For example, if we randomly generated a 2 and a 6, then tanks 2 and 6 will receive T1. All right, we're going to repeat this process until all treatments have been assigned. So for example, you're gonna randomly generate 2 more unique numbers between 1 and 12, ignoring whatever came out in the first set of random numbers. And those 2 unique integers between 1 and 12 will receive treatment 2, so on and so forth. I had to add this comment to be sure to ignore repeats from previous steps as well. Okay. That way we can ensure that no tanks will receive more than 1 treatment. Of course, we wouldn't want that. Now, I've noticed that in a lot of mock exams that I have seen, they bring up this concept of replication. And I just wanted you to understand that this idea of replication, which is one of the 4 principles of experimental design, replication is satisfied once each treatment is applied to more than one experimental unit. Okay, so for example, treatment 1 is going to be applied to 2 tanks, just like so is treatment 2, treatment 3, so on and so forth. The fact that each treatment is being applied to more than one experimental unit satisfies the replication principle. Now, of course, you'd like to see a little bit more replication than that, but at least there is some replication going on. Okay, part C goes ahead and asks about, where are we at? Okay, there we go. Give one statistical advantage to having only tiger shrimp in the experiment. Explain why this is an advantage. And part D is similar. It says one statistical disadvantage to having only tiger shrimp. Now, with problems like these, it's very important that we use context and also use proper statistical vocabulary. Okay, so an advantage to having only tiger shrimps is as follows. By using only tiger shrimp in this experiment, we reduce the chance of sampling variability. The key term, the key phrase there being sampling variability. And actually, I should say we reduce, not the chance of, sampling variability is going to happen no matter what, but we reduce sampling variability. In other words, our results are more likely to accurately reflect the effects of salinity and nutrients on the tiger shrimp growth. So if we had other types of shrimp and we were randomly assigning treatments to other types of shrimp, like we just had groups of many different types of shrimp, there's an additional layer of variability in there. Different shrimp may react differently to different salinity levels or nutrients. All right, so the fact that we're focusing on one type of shrimp will reduce sampling variability. Just as a side note, by the way, this has nothing to do with experimental design, but it has to do with sampling from a population. So if we have some population and we want to randomly sample from this population, a question might say, oh, we decide to stratify on a certain variable. And what is the advantage of stratified sampling? The answer is always going to be that stratified sampling reduces sampling variability, okay? So if a question brings up that the sampling method that was used was stratified sampling, and if they ask why that's advantageous, the reason is because it reduces sampling variability. Of course, make sure to describe this in the context of whatever the problem is. Always, 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 always answer in context. All right, so I just wanted to make that point because it seems to come up a lot, to be quite honest. Stratified sampling advantage is that it reduces sampling variability. Similar to, in this case, using only tiger shrimp. All right, and the statistical disadvantage, by using only tiger shrimp in this experiment, we reduce the scope of inference, right? So unfortunately, yeah, these results are great for tiger shrimp, but not very helpful for other types of shrimp. In fact, it wouldn't be really a good idea to apply these results to other type of shrimp. As mentioned before, other type of shrimp might react differently to different salinity levels. All right, folks, so that's all. The big day is tomorrow, just a little over 24 hours from now. I just want to say that, you know, you've put in the work. You just have to trust yourself at this point. All right? You'll be fine. You'll be fine. All right, folks. Any questions, of course, feel free to email me. And I'll have SGI twice today. And I'll be available pretty much by request all day today and all day tomorrow. All right. Take care, ladies and gentlemen. Bye.